I'm from Shield AI. Our mission is to protect service members and civilians with artificially intelligent systems. Our objective in our development and pursuit of that mission is to create our Hivemind framework, which is a foundational framework that seeks to create resilient intelligence capabilities to operate in the most challenging environments and conditions. Fundamental to our approach is this underlying thesis that it's possible to create a foundation that is applicable across all platforms and all domains, and the tools that are necessary to specialize. So amongst those foundation frameworks and models, the ability to deploy this intelligence and to deploy it in the most challenging conditions and iterate upon that performance rapidly and efficiently. To that end, we've created our Hivemind software platform that has both the capabilities that run on the edge that allow these systems to operate as one or many and to think for themselves, as well as the tooling and infrastructure necessary to iterate and permute on those capabilities and to improve upon that performance. For our customers, we need to take a step further because of the nature of the class of platforms and the operational conditions in which they operate. So we have to look at beyond just what are the intelligence capabilities running on the systems, but how do we think about everything from end to end? Conceptualization, operational analysis, design, development, testing, evaluation, verification, validation, and ultimately operationalization of that capability. Over the last many years, we've developed our Hivemind software platform, as I was just noting. This framework is designed from the perspective of a highly modular, highly extensible set of software development kits that enable not just Shield AI, but our customers to apply these capabilities and accelerate their own development to deployment. Fundamentally, we have to think about everything that the last speaker just called out in terms of those important technologies and capabilities, but we need to take the step further to automate and streamline those processes to make sure that we are able to actually approach questions like, how do you certify this system? How can you assure the performance of this system? How can you enable and ensure that the operations on that system will meet our expectations, meet our requirements, support traceability, auditability, formal configuration management, and similar. So to that end, within this framework, we've really thought about all of the different stages of development and the streamlining of that from those early stages of developing the AI pilots, iterating on that performance, testing and evaluating under many different classes of scenarios and missions, but then going on further to really instrument, diagnose, and enable those underlying foundational requirements that our customers require. We've integrated capabilities that allow these systems to operate in the most challenging conditions, and that includes where no external information is available, where it can be very difficult for humans to be in and on the loop, and in scenarios where one requires multiple different systems, multi-domain, and heterogeneous to be able to work together. And finally, through the design of this software platform, we've really pursued a strategy that allows not just Shield AI, but our partners, our customers, and allies to be able to leverage these capabilities to build out their own sovereign capacity, which is so important from a strategic perspective at a global scale. At this time, Shield AI and Hivemind are working with nearly every prime, defense prime within the US, and similarly within Europe, the UK, East Asia, Oceania, and beyond. In terms of the framework itself, there are two key areas or two key parts of it that I called out earlier, that edge-level intelligence, as well as what we call our autonomy factory or forge, that integrates all of the different stages and workflows that I just described. This is a very standard kind of framework in terms of training, simulation, and deployment. And here's an example of where we've integrated NVIDIA and the Omniverse to be able to really build out certain sets of capabilities and simulate and train these capabilities at scale. As we deploy on every new platform, every new domain, we're thinking through and establishing tests and trials at a very large scale from a synthetic data generation perspective, iterating on the performance of the systems, what those systems are deciding to do, or what the systems are deciding to do, how they're going to do it. And then we're integrating that all together, of course, to generate those edge-level deployments that are running on those platforms. As I noted, our platforms have operated in most recent operational conditions and conflicts, and is currently being used at a global scale. Additionally, in terms of where we're going into the future, I think the main item that I would call out is we've really focused on how to proliferate Hivemind to as many platforms as possible, to work with as many partners as possible, to be able to iterate and deploy on large classes and numbers of systems and platforms. There are many different videos that I could show you of the different types of platforms we've deployed on, everything from quadcopters to uncrewed jets, so modified F-16s, systems that are operating 24/7 sorties and beyond. Now we're focused on expanding our attention beyond the autonomy development lifecycle to the full autonomy lifecycle, making it possible for Shield and our customers to be able to go from design and development to results and to outcomes rapidly and efficiently. We're expanding across that autonomy lifecycle now, and we're expanding across more domains. I called out earlier air and water examples and land, but we're also now expanding into the space domain. So this is really exciting. It proves that original thesis that it is possible to build out this type of framework, to scale it, to operationalize it, and to ultimately drive toward meaningful mission impact. Thank you.
Talk about AI skills for every robots. Everyone is trying to build general purpose intelligence. And I'll take a few seconds to distinguish between intelligence and skills. There are 8 billion people on this planet who are intelligent. Few of them have the skills to drive a car, and even fewer have the skills to fly an airplane. I want my robot to be skillful. Intelligence is a good, it's a good golden compass. But skills is what make these robots useful now. I have spoken to, let's see, not skillful. All right, so I have spoken with, I would say, hundreds of large enterprises, right? And these are enterprises in commercial sector, in manufacturing, in energy. They have already bought robots, UR5E arms, Boston Dynamic dogs, now humanoids. And most of these robotic form factors are not skillful. In fact, if you look at the modern way of building AI, which is deep learning centric, which is reinforcement learning centric, which is foundation model centric, across the board, I have yet to come across a single deployment, right? And this is interesting. They spent millions of dollars buying these equipments, these GPUs, but they don't have the expertise. Between fragmented infrastructure and scarce expertise, no one is getting to deployment, right? And again, this is really, this is G1. We've already seen that. We've seen this guy do flips, kung fu moves, but it cannot cross this ledge, right? It cannot cross this ledge. Why? Because this perception to action loop is a very difficult technology for most of the organizations to build and to deploy. For every 20 machine learning engineers, probably there is only one, maybe even less, who can work on robotics and deep learning. Less than 1,000 people worldwide, I believe, have the expertise to take deep learning policies and deploy and work with the robots. So then, how do we create value? We are selling hardware, we are selling GPUs. If they are not getting to deployment, if they are not making value, then I think we need to figure out how to solve it. And that's what Grid does, right? Instead of develop, refine, and scale, we have turned things around a little bit differently. We say, if we have an enterprise that has already gotten all these hardware, can we get them to deployment in 15 minutes, right? So for instance, imagine a large car manufacturer, and they have a collection of Franca or UR5E arms. You show up at the factory floor, give them a container, and it's doing, say, generalized pick and place as a skill in 15 minutes, right? And that's what we do with Grid. Grid is a platform which is integrated across a number of robotic form factors. There are 40 plus different OEMs. These are robots that have already been in the field and sold in numbers. And all of these robots, when they are plugged into Grid, they have these AI skills. So for instance, generalized pick and place for your arms, indoor locomotion, safe navigation, those kinds of skills that are extremely important for you to go and start building value now. And of course, you deploy it fast. Maybe it requires adaptation. It requires adaptation because, your car manufacturer, you need special kind of gripping for your carburetors or airbags, or you are a quadruped and you are deploying it in an oil rig and it requires certain considerations. So those adaptations, again, if you have the right skills on grid, you can adapt in less than a day. And again, the way grid is architected that allows seamless scaling. If you have things working on a one robot, you can scale it to 1,000 robots with just a flip of a bit, right? Again, here is an example of a grid in action. So these are all robot form factors that you can buy now. Unitary quadrupeds, a humanoid, UR arms, modal AI drone, and they are exhibiting skills directly from grid, which otherwise enterprises will take, months, if not years, to train themselves. Specifically, in terms of technology, what's happening is that there is a container, a thin client, that's running on these robots and calling grid. Grid is your repository of AI skills. Grid can be hosted on a commercial cloud, great for hotels and hospitals and homes, or on-prem, right next to your factories, for instance, factory robots, or on the edge as well. For instance, we ran a workshop yesterday where Ghost Robotics robot was running grid right from the edge, right? But this is what allows robots to get skills right away. Now the question is, where do these skills come from, right? So these skills come from, again, we are primarily an R&D team, so a lot of these skills are being built in-house through some of the latest and the greatest research that's coming out. In AI, one of the biggest revolution is happening because from research to deployment, that cycle has been shortened really well. In robotics, that hasn't happened, and grid solves it. If you have a model, if you have a workflow that's coming out in the literature right now, we take all the effort to get in and reveal it on grid ASAP. So what you're seeing here is some of these skills, for instance, right? Some of the very well-capitalized humanoid companies would die to have, but it's in grid right now. If you are using G1, for instance, you should go and come and talk to us, and we can figure out how to work together. Again, the new programming paradigm, for instance, using agentic infrastructure or Copilot, all of those workflows is enabled on grid because of the design of it, right? We have MCP servers, we have code gen, all those capabilities. So once you deploy, if you have an in-house robotic teams, they can use all these workflows to further refine it and adapt it. I'm going to play one example, right? I talked about getting AI skills, but what happens? How do you adapt it? And that's where a lot of NVIDIA ecosystem comes into the play. So let's see if this guy has a volume in it. It has in here. Okay, I'll walk over it. I'll walk you through it. So imagine you are a large car parts manufacturer. Airbags. Your computer vision models have never seen these airbags, and you want to go and pick and place, a generalized pick and place. So there is a workflow on grid that allows you to create simulations. Again, we had previous sessions talking about Gaussian splatting, but all those technologies are available on grid, so you can pull these models, create simulations quite rapidly. As I said, our goal to adaptation is less than a day. We do it through our engineering expertise as well as expertise on the customer side of things, and then of course you have simulations and one-click deployment onto grid. Adapting these kinds of parts, generalized pick and place that models had never seen before, you can basically do it on grid. The technology behind it is what we call this grid stack. We are innovating across robot models inferencing, creation of AI skills, composition of those AI skills through modern coding methodologies, reinforcement learning included, and then deployment. Why are we still stuck in the ROS era? ROS was invented before deep learning, before cloud. Modern ways to deploy these skills, right? There are way better ways we can architect. And one of the ways we have done is deployment that is agnostic to form factor, as well as spans across a number of different OEMs that are present out there, right? So, I will conclude with, basically, if you are working in robotics and you want to make your robots useful fast, please come and talk to us, because that's what the mission is, right? There have been plenty of robots that are sitting on the shelf collecting dust. Many of these robots stay in the innovation office. They are never deployed. They don't go beyond POC stage. And as an industry, unless we change that, unless we make these robots useful, I think we won't be able to scale or achieve the kinds of promise that this technology makes. So thank you very much.
Always a huge pleasure to be at GTC. I think it's really the only place in the world that we really see that confluence of the latest in both AI and robotics coming all together. So great to be here. Today, I'm going to talk a bit about what we're building at Field AI, which is robot-agnostic foundation models. These are models that can be deployed across a variety of different robot form factors. They're agnostic to the actual embodiment itself across different environments in a risk and safety-aware fashion. The story of our company actually began in exploration. So at NASA JPL, our CEO and a core set of our team members were pushing the boundaries of what was possible with robotics autonomy, deploying the very first legged autonomous robots in Mars analog caves, ranging from volcanic lava tubes all the way to underground cave networks. These were very complex environments, very challenging environments, handling complete darkness, unpredictable terrains. And these were also environments that are not very easy even for humans to traverse. The team was working on this to really push on the boundaries of one of humanity's oldest questions, which was, how do we actually search for life beyond Earth? But at the same time, we were solving another different problem, which was, how do we enable robots to survive in settings which is very difficult for humans to? As a result of those progress, our team was also selected as one of the few members that actually joined the DARPA Subterranean Challenge, which was, at the time, the latest in the cutting-edge DARPA Challenge series, which was pushing the boundaries of what's possible in robotics autonomy. And here, our team was deploying fleets of robots, so heterogeneous teams of robots ranging from wheeled to legged quadrupeds, all the way to drones, that were collaborating with one another, communicating with one another, exploring environments with no prior information, mapping those environments with no access to GPS, just raw autonomy in action. And what we learned here was that not only can you have individual robots that are deployed using a unified architecture, but you can actually have them coordinate with one another and solve problems that they otherwise can't in an individual fashion. So all of those learnings combined, now what we've enabled at Field AI is technology that's focused on risk-aware and uncertainty-aware autonomy. That is finally taking robots out of labs and controlled settings into uncontrolled, unstructured environments, human-purposed environments. These are settings that haven't been designed and optimized for robots themselves. And you can see some of the deployments that we have in action here across a variety of different domains and robot form factors. At the core of our technology is actually a very simple concept, which is a unified robot model that is able to be deployed across a variety of different form factors. And the first layer of this is actually what we call physical AI, which is focused on learning fundamental skills related to keeping the robot stable, having it maneuver, navigate in the environment, manipulate the environment around itself. And this itself is a very difficult research problem. A lot of different cutting-edge research institutions are actually pushing on the boundaries of this alone. And this is also where we push very heavily on the simulation side, using tools like NVIDIA Isaac Sim and Lab to train these policies in simulation, to really test them in virtual environments before we actually deploy them to the physical world. On the left here, you can actually see a demonstration of one of our policies. So here, it's actually a completely blind policy in the sense of the robot is using its proprioception, its sense of feel in the environment, as somebody is giving it commands to basically maneuver in this very dense and complex setting. But once we add perception in the loop, not only can we do very dynamic maneuvers, but we can actually understand the state of the environment in high frequency, all on the edge, happening at hundreds of hertz. And lastly, now we're pushing on the boundaries of humanoid local manipulation as well. So not only having humanoids that can walk around, but that can actually manipulate objects in the environment, can actually change the state of the environment around themselves. But it's one thing to have robots that can be stable and walk around and do crazy flips. It's an entirely different thing to actually have them be integrated into the workflows of our customers, to actually deliver value to them. And that's the layer that we call operational AI. So in operational AI, that's where we bring in context, long-term memory, reasoning, really a deep understanding of what are the tasks that are useful for our customers, what actually would be helpful for them in terms of delivering value that maybe an intern would, or an actual human worker that they don't have access to would. And that all fits within this layer. And this combination of these architectures is what actually enables us to deploy a variety of different robot form factors that you can see here across domains like construction, oil and gas, security, data centers. All around the world, we've been field testing and deploying many, many different types of robots at dozens, hundreds of different sites now. And now actually moving from the smaller form factors all the way to full-size, passenger-sized vehicles as well. Our autonomy is actually enabling this type of form factor too, where we actually basically hand off our stack to DARPA, the sponsor in this project, and we're able to traverse tens of kilometers with no prior information about these very complex environments. So no maps, no GPS, all of the decision-making happening right on the edge. And for us, this is a true test of, a stress test of autonomy, right? We're pushing the capabilities of these vehicles to the edges of their physical limits, to the edges of what even a human driver would be able to achieve. And the way that we actually enable this is by solving a very classic problem in robotics deployment, which is a dependency cycle issue, where you need very rich data to actually train models that can be deployed, but at the same time, you need to have good models such that you can actually go in the real world and gather that data. So instead of trying to break this dependency cycle, we actually embrace it. In our case, we actually go into the belly of the models themselves. We revisited the entire architecture of our models, and into them, we actually implemented uncertainty and risk awareness in a probabilistic sense. So when we deploy our robots, they have a sense of the distributional nature of the environment around themselves. They actually are able to push and probe into the edges of the environment to get the long tail of the data that's the most diverse and high quality data, such that with every deployment, when we go back offline and train these models, they're getting better and better and better. And all of this would, of course, not be possible without a deep integration into NVIDIA technology. So, of course, we're very heavily on the physical AI side, leaning into Omniverse Isaac Lab and Isaac Sim, training these policies. We're deploying on edge. So the autonomy that we're actually demonstrating in all the videos that you see here is running physically on the edge of the robots themselves. And because of Jetson, for example, we're able to run very complex policies on low power, very small form factor robots now. And of course, underpinning all of this is massive training and compute enabled by NVIDIA GPUs. And because of this ecosystem, fundamentally, we're able to go from that concept to deployment state orders of magnitude faster than we would otherwise be able to. As a result of all of our technology, now we've really been pushing beyond the traditional scaling limits in deploying robots. So as mentioned earlier, to date, we've field tested at hundreds of different sites around the world. These are all real world environments. And these are also environments that are very unstructured in nature, right? So we can't actually go in and install infrastructure, optimize them for the robots themselves. We have to be able to deploy basically on day one. Now, looking into the future, what we're really excited about is not just that we're enabling better robots. Fundamentally, what we see is that we're transforming the nature of physical data collection itself. Just like Google was able to collect and digitize almost every road in the world, what we see here is a deployment where we have a network of robots able to interface with one another, collect data, and really be deployed to any unstructured environment on Earth. And to us, it's also a very key societal problem, because in every sector that we deploy, what we're seeing is massive labor shortages on the order of millions, whether it's construction or oil and gas or anywhere else. And to us, by training and enabling these generalizable and cost-affordable robot platforms, not only are we able to help address those labor gaps, but also we're able to increase the reliability and safety of these operations, especially around humans as well. And that fundamentally is the future that we're building at Field AI. So thank you very much again. If you're interested to see our AI in action in these final few hours, please visit us at booth 459. So thank you.
Thank you very much for having me. So to sort of clear the air, so I'm an academic, so I snuck into the session here on startups, but humor me, I'll tell you about some of the research we're doing in the lab. It's actually very related to some of the things you just heard about. All right, so just a little bit of context on me, the MATLAB, and some of our prior work on field robotics. So we really started in earnest after the last major earthquake that happened in Mexico City in 2017, where we were deploying, this is me with the Mexican Red Cross, deploying snake robots to actually go, this was a collapsed building, so this was like 3 days after that happened. Into some work on the DARPA Subterranean Challenge, like some of the other folks who were just speaking, DARPA Racer program, which is the full-size vehicles, and then some work we're doing on heterogeneous autonomy with ARL. So one of the things, if not the most major thing that I've really learned and my students have really learned throughout these projects and throughout the years is when you deploy robots in the real world, unexpected things are going to happen. Here you can see a very expensive robot that it's found its way into a hole in a field in the middle of Ohio. And then almost surely, after you experience these unexpected events, you're going to have a scenario that looks something like this, which is now a group of engineers. We know that the robot drove itself into a hole, but now you got to figure out why. So this is a challenging problem, and we'll come back to our poor group of engineers. All right, so let's just take a quick step back and think about some of the events that might lead up to my robot finding its way into a hole in the middle of Ohio. So I have the real world where I want to deploy my robots. Different robot here, but robot, real world. Now I have access to a simulator, right, through NVIDIA Isaac Sim, and a reasonable thing to do is to go and simulate my robot, try to learn a policy, and then deploy that policy on my real robot in the real world. Let's say my policy here is I want to have my robot avoid boxes. Cool. All right, well, it's not going to take me very long, or my robot very long, to encounter not box. Maybe I'm in my field in Ohio, and I see a fence post. So, all right, now my robot has issues with fence posts, but I'm not dead in the water yet. I can go and collect data, as we just heard some of the other speakers speaking about. I can create this loop of collecting data, pumping that back into my simulated world. So now my simulated world has boxes and it has fence posts, and lo and behold, I can retrain a policy, deploy that on my real robot, and now I avoid boxes and I avoid fence posts, all right? I'm having a good day, so I collect lots of these samples. Like the last speaker was just speaking about, and what do? I can try to get my simulated world to match my real world. And again, I mentioned in several of the other talks here, it's not gonna actually take that long of trying to pursue this model before you end up, again, with the notorious long tail ends of the distribution. Things that don't happen very often, but are still probable. So in this case, I've trained my robot to avoid all sorts of positive obstacles, and boom, negative obstacle. It makes sense once you see it, but it's very difficult to predict this a priori. So, of course, right, this is due to this problem that the real world is actually much, much more complicated than something we can just go out and collect some data and try to recreate what's actually going on in the real world. So, the sort of main thesis here is the reason that this is right, physical interaction. When you have a robot that's going out, and it's not just walking on flat ground, it's walking upstairs, it's driving through a field, that type of physical interaction is in some sense infinitely uncertain. You're never going to be able to predict what's going to happen next in all of these scenarios. So if I want to train robots in a simulated world, and I want to learn policies that I want to deploy on my robots in the real world, again, it stands to reason that I'm going to need some way to get my simulated world to actually match the distribution of events and uncertainty that I see in my simulated world. All right, so that sounds a little bit difficult, but let's come back to that. Let's look at a specific example of a robot. Again, similar robot to what you've seen thus far in the session, a spot robot, and I want the robot to go upstairs. So lo and behold, using the NVIDIA tools, Isaac Sim simulation, I can go and I can simulate a bunch of different worlds, and for sure I can now get my robot to go and climb up, not just this set of stairs, but all sorts of different sets of stairs. Cool, that's good. I'm having a good day. But now I introduce a slight perturbation into the system. So I add clutter onto the stairs. What's going to happen? Is my policy that climbs stairs, how's it going to work? What's going to be the performance? And again, this to you and I is not that major a perturbation. I've just put some stuff on the stairs, but how is the robot going to interact? So if we really dig down into this, and we think about specifically what makes this challenging for a robot, this type of generalization from just stairs to cluttered stairs. Again, doesn't seem that difficult to us, but to a robot, I will tell you that this is a very challenging problem. So the first thing is I have an autonomous robot. It has onboard sensors, onboard compute. It's out in the world. I will tell you, at least in my experience, robot perception and mapping is not a solved problem. So there's all sorts of different challenges here. But in the context of this problem or this example, right, the robot, it's going to have trouble walking up the stairs if it can't tell what is clutter and what's a stair. Most of the robots, or certainly all the robots I've ever worked on deployed in the field, have some explicit notion of a planner, the decision-making process. And there's typically going to be a person, an engineer who's behind tuning and designing this planner. Right? And the planner is going to fundamentally be biased by the decisions made by the person who designed your planner. It could be overly conservative. It could walk really fast. These things make it very difficult to predict how your robot's going to react. And then the real doozy is at the execution layer, your controller of your robot. So typically, right, our controllers for our robots are based on some pretty rigid assumptions about how the robot's going to interact with the physical world. And these are the sort of unknown unknowns, right? Things like ice on the stairs, things that are very, very difficult to predict a priori. They might be very difficult to sense with my onboard sensors. So if we really break this down, what we're talking about is this problem, this type of generalization is difficult because you have all of these different forms of uncertainty in the system. Aleatoric uncertainty, the known unknowns, things like sensor noise. What we're calling performance uncertainty, where you don't know how the robot's going to react in certain scenarios just based on its decision-making process. And again, sort of doozy here, the epistemic, the unknown unknowns, starting to quantify the tail ends of the distribution. So realistically, back to my engineers, the thing that really ultimately makes this problem challenging is not that these different forms of uncertainty exist, it's that they typically exist simultaneously and they're intertwined. So how am I going to get my group of engineers to be able to go and figure out what specifically caused my robot to drive into a hole when I have all of these different forms of uncertainty in the system? So these insights, whatever this work, the pain we've been through, numerous projects, has really led my group, and similar to some of the other ideas that you've heard here today, to really focus much more explicitly on a tight coupling between perception and action. These are some of our recent publications that go into the details of what you're looking at here. Estimating stairs, so the perception side. Here's a stair climbing policy. So back to our real to sim to real transfer loop here. So this has really led us to what we believe is our key insight, and this is something that we refer to as a task-relevant belief. And this concept that if I have a particular task, I can take all of the infinite forms of uncertainty that exist in the real world, and I can start to filter those down into a much more finite representation. What does that mean? Good question. Back to my robot on stairs example. So my robot knows how to climb up and down stairs. If I could push these obstacles out of the way, this is a solved problem, right? My clutter no longer, I don't have to worry about it. So now what am I going to do? Am I going to train a policy to go and move the obstacles out of the way? All right, that sounds reasonable, cool. So what do I need to know in order to train that policy? Do I need to know the friction of the stairs, the density of the obstacles, the mass of the obstacles? Right? If I want to go and solve this problem, I just go move the stuff out of the way. I don't worry about these low-level quantities, the uncertainty over them. So arguably, what we do is we directly reason in what we're calling here a task-relevant feature space. I reason directly about the movability, not the friction of the stairs. So a task-relevant belief is the space of is a probability distribution over a task-relevant feature space. So the main concept here is if I'm able to directly reason about movability, can I basically marginalize over all of the other uncertain parameters in the system? Saying this another way, if I can directly estimate movability, can I show that my planning task of walking up the stairs from Rhode Island, sorry, stairs makes the planning task conditionally independent of all of the other forms of uncertainty, the lower level forms of uncertainty in the planning problem. Movability depends on stair friction and all these other properties, but if I know the movability and can estimate that directly, can I show that I don't need to worry about these quantities? And furthermore, when I go simulate the real world, I don't need a high fidelity simulation if I can just reason in this in-between latent space. The latent space formed by the task-relevant features. So what does this actually look like, and how do we accomplish this using tools, software, and hardware tools from NVIDIA? So we go out and we train an initial policy. And you can actually, and we deploy the policy on the AGX embedded platforms. And you can see here that some of these trials are not successful. So that's fine. What we do is we record all of this data, and we start to disentangle how these different forms of uncertainty in my task-relevant belief space contributed to my robot to either positively move the objects or to miss the objects. Then very critically, we track and we quantify all of these different forms of uncertainty during task execution. So we extract task-relevant beliefs, from which, right now we have our data. Now we can actually go and use our uncertainty-aware data to now train simulators or a belief space simulator, which is what you're looking at here, which is using Isaac Sim. But we are now, again, what we're simulating is a task-relevant belief dynamic, as opposed to just thinking about simulation as a deterministic thing where I go take data from the world, try to recreate a sort of conventional notion of a digital twin, or more geometric representation of the environment. Now we're starting to use this in-between space as the basis for thinking about doing uncertainty-aware simulation. So when I go and now deploy my policy on my robot, my policy, again, very similar to some of the other topics you heard about today, is risk-aware. It understands the underlying uncertainty, and in particular, it understands the dynamics of how uncertainty propagates during task execution. So I go and deploy this. Oh. Uh-oh. Oh, there's a slide missing. It was the punchline. So anyway, it was a version of this. Here you can actually see the green represents, that's a bummer. All right, so the green represents the movability of the obstacles. So the task-relevant belief space here is the position of the obstacle, or the obstacles on the stairs, and then the movability over it. In this case, you can see the robot is, both obstacles are movable. It's more interesting when one of them's not movable. But you can see here, connecting the low-level policy to now a task-level executor. Everything that you see in this video is trained in Isaac Sim and then deployed directly on the robot. All right, so what comes next for us is great, Spot robot pushing stuff off of stairs is cool, but ultimately, where do we see this going? And obviously, we want to take this concept and these task-relevant beliefs and generalize these to other systems. So this is some work I'm doing in space. This is actually from the DARPA RACER program. This is one of my prior students. And yeah, with that, I encourage you to sort of track the progress of me and my lab as we go and we figure these things out. Thank you very much for your attention. I hope everyone has a great evening.